So let's pick up where we were. Just had a few seconds and didn't want to try to squeeze this in. So again, the boundary layer is defined as this thickness here, where you achieve 99% of the average speed. So basically, you reach a point where we can't measure a noticeable difference. You move up far enough in the y direction, and if we keep measuring the speed out here and out here and out here, we no longer notice a noticeable difference. We keep getting essentially the same speed measurement over and over again. I've actually been, I actually TA'd as an undergrad for a freshman level engineering experimentation class, where we actually went, we had a wind tunnel set up, and the students actually had, we'd found velocity probes, little wands, look like kind of like antennas with little tips. They had little velocity sensor tips at the end of them. And the students could actually, we had ports in the wind tunnel where the students could actually take this velocity probe, let's say my pen's like the velocity probe, and they could actually stick those velocity probes into this, these holes in the side of the wind tunnel, and they can measure, say, the velocity right there. And then they can move in a little bit further and measure the velocity there, and move in a little further and measure the velocity there. And they were actually able to then, they had data then that they could actually, measuring how far, how far in they were, basically by measuring this, the length of the pin back here, they knew how far this length is. So they could tell how far in they were, right, their Y value, and they could actually measure when they started detecting the boundary layer, when they kept getting the same speed measurement over and over again. So it was actually a really cool experiment having them actually measure the boundary layer. I wish we could do that, but here we are. So we'll make this work. But that's the definition of the boundary layer. That's what it represents. Is you're going to have this area where the fluid is slowed down, or the speed is going to be different than the average speed. And this thickness is, by definition, where you have 99% less, more than a 1% difference between the average speed out here. Anything inside of that is the boundary layer. How thick is it? It depends on the fluid. It depends on the surface it's flowing over. It depends on how fast it's going. But if it's air being pulled at a fairly high speed, we're talking about millimeters. I mean, it's actually really difficult to measure without good equipment and good experimental methods. But that's kind of the basic idea. Now, what I'm saying here, so in our text, chapter 10, chapters 9 and 10 in your text, I don't know if you've noticed, we've gone from 8 to 11. We've skipped over chapters 9 and 10. Chapters 9 and 10 talk about Navier-Stokes theorem. And that's really good, important stuff for those of you going into aerodynamics. It's, I don't know, without having differential equations, without assuming you've had all of your calculus and differential equations done and done anything useful with that, it's a bit of a challenge. It's not impossible for engineers at this level, at the junior level, to work with, but it is definitely a challenge. It definitely makes the fluid mechanics course a lot more challenging to incorporate it. I'm choosing, especially this semester, because we're in this online format halfway through, we're definitely not going to incorporate it this semester. But when you go back and look in chapters 9 and 10 within your text, we're in the Changle and Cimbala text, they talk about the Navier-Stokes theorem there. In chapter 10, they derive the Reynolds number, they actually derive expressions for the boundary layer as functions of the Reynolds number, which in the Reynolds number REX, we say that is equal to rho V X over mu. Right, and what we're saying there is, notice again on this plate surface here, we're saying that, as you move further along in the X direction, this boundary layer actually kind of moves back a little bit. And so we're saying the Reynolds number at a different X location is going to be a little bit different. So as you get further along this plate, you're going to have a higher Reynolds number for that plate. So the Reynolds number is out here at the very leading edge. The Reynolds number here would be 0. And the further along you get, the higher the Reynolds number gets. And what we what we would find, right, what we would find if we could actually measure this and visualize it, if we have fluid flow up here, what you would find is right here at x equals 0, you would have pretty laminar flow. And the further along you move, because the Reynolds number is getting higher, the more turbulent the flow will actually get. I think you see, I think in your text they talk about if you light a candle or you light a match and you blow out the match and you watch the smoke plume come off the match. Right here, just right off the match, that smoke plume, all the smoke's moving together in a straight line. All right, so just go grab your match and do this very safely. All right, don't light a match somewhere you're going to catch something on fire. But if you can safely light a match and blow it out, and then watch what the smoke does. Right here at the point of the smoke origin, the molecules are moving in a laminar fashion. They're all moving kind of in a straight line. And as you move further away from that origin point, you'll notice more and more turbulence. And that's what we're saying here with the Reynolds number. As you move further along, you're going to most likely see more and more turbulence, higher and higher Reynolds number, the further you move along this plate or this surface. Okay, and so what we find is the boundary layer, because of that behavior, the boundary layer also, the further we get along here, the thicker the boundary layer will get to a certain point. Once we reach full turbulence out here, then the boundary layer stops getting thicker. Right? But up to a certain point, the boundary layer does get thicker as we go along the x value. In Chapter 10, they derive expressions for trying to predict the thickness of that boundary layer as a function of the Reynolds number, which the Reynolds number along the x direction. So the Reynolds number along the x direction, you can see here, is rho v x over mu. Okay, so instead of characteristic length being the diameter, characteristic length here is being the x length, the x position. Okay, so those expressions, and here I've got a blank slide on a smart board. I would normally write those expressions. I'm just going to write them on paper for you here. Okay. So those expressions, and I've got those just barely off screen here. I believe I've got those copied correctly. The coefficient of friction in the x, which this is a function of the x value, and it's also a function of the Reynolds number, which the Reynolds number in the x is actually a function of x, so it's really just a function of the x value. That coefficient of friction along the x value there is 0.664 over this Reynolds number x, and it's the square root. So this is raised to the 1/2 power, the Reynolds number is. And remember, that Reynolds number x is this rho vx over mu. That's this guy. Take the square root of that, invert it, multiply by 0.664, and that gives you this coefficient of friction if we have laminar flow. Okay, so that's if at this particular x location you're in the laminar region. And as we move, if we achieve turbulence, if your Reynolds number as you move along the x-axis gets high enough to achieve turbulence, in the turbulent region we tend to observe 0.059 over the 5th root of the Reynolds number. So it's REX raised to the 1/5 power, or the 5th root of the Reynolds number, rho Vx over mu. Again, that is in the turbulent region. Okay, and now that's okay if you want to know at one specific X location. If I want to know what is the coefficient of friction right here, and then I can also say, well, the coefficient of friction out here, if this is the turbulent region, then I've got a coefficient of friction that I can compute this way. And that's nice, but really what I need to know is what is the coefficient of friction across the entire surface? Right? How do I find the coefficient of friction across the entire surface? not just one single x value. Well, to find that, I need the coefficient of friction across the entire length, or the average coefficient of friction across the entire length. Well, what we do is we're just going to integrate from 0 to length L across the entire length, and I'm going to multiply by 1 over L because it's going to be an average. So 1 over L times this integral from 0 to length, the coefficient of friction at every x value, and integrate that with respect to x, or along the x-axis. This will give us the average coefficient of length. Now, these are not hard to integrate, obviously. We've done way worse, hopefully, in a calculus class, but somebody's already done it for us, and we just have to look at it and make sure, okay, that makes sense. If it's laminar, if the entire plate is laminar, it's 1.33 divided by the Reynolds number computed out at length L. Take the square root of that quantity, square root of the Reynolds number computed out at length L, if the entire plate is laminar. If the majority of the plate is in the turbulent region, that's 0.074 divided by the Reynolds number computed out at length L raised to the 1/5 power. All right, again, this is any particular x value if it's laminar, and if the entire plate is typically in the laminar region, or just barely, the end of it's just barely in the turbulent region, this will get you a really good approximation. If the very end of the plate is, if the majority of the plate is in the turbulent region, this guy will work just fine. Okay. Now, I think I say here. So what they'll tell you there is the critical value between laminar and turbulent. They're saying here is anything greater than, what are they saying? They're saying 5 times 10 to the 5. Right? So anything greater than this is turbulent. Anything less than 5 times 10 to the 5 is laminar. At least we could expect that. So we're saying if you compute the Reynolds number out at length L and you get less than 5 times 10 to the 5, then essentially the entire plate is in the laminar region. Now, if say maybe 90% of the plate, so if you come out to 10% of the length, you compute the Reynolds number at 10% of the length, and you get a value greater than 5 times 10 to the 5, you're probably better served to just use this quantity here. Now, in the text, they say, well, there is kind of this magic in-between region. So what you want to do is compute the Reynolds number out at the length. If it's less than 5 times 10 to the 5, the entire plate's in the laminar region. Just use the laminar quantity. And they're saying here, look, if you go out to the length L and compute the Reynolds number and you find 1 times 10 to the 7, 10 million, right? 1 times 10 to the 7. Just assume the entire plate is turbulent. So that's what this text recommends, is just go to the end. If you get 10 million Reynolds number at the end of the plate, assume the entire plate's turbulent, and use this expression here to find the average coefficient of friction for the entire length. That'll be fine. And then just plug that into your drag force equation, and we move on. If you're in between these two, so if I compute the Reynolds number out at the length out at the end of the plate, right, and I find a Reynolds number between these two values, they're saying it's kind of in between. Right. Half the plate, and I'm going to have to pick up the next video there. All right, so I'm going to pause it. I'll pop here.